a resistance and capacitor in a circuit. A resistance and capacitor in a circuit, and the capacitor is charged before the resistor is placed into the circuit, and we'll calculate later on how the discharge occurs. So 140 microfarad capacitor, 980 microcoulombs, and the resistor. Let's draw the circuit for this. The capacitor symbol is just two parallel lines, and we come out to a resistor. So 140 microfarads and 12.6 kiloohms for the resistor. So that's going to be the circuit we're working with. We actually want to do a separate calculation before we calculate the discharge. If we would just have isolated 140 microfarad capacitor that's charged with 980 microcoulombs, what's the potential across the capacitor? We don't need to consider the resistor for this calculation. Instead, we use Q equals CV, the charge on the capacitor, on the magnitude on each plate, Q, equals the capacitance value. This does not stand for coulombs. This stands for farads of capacitance, and the voltage, the potential difference between the plates. But we have the numbers to do this calculation directly. So 980 microcoulombs equals 140 microfarads times our unknown voltage. And you can see that we can avoid use of 10 to the minus 6 in our calculator. There's a micro on each side of the equation. Let's cancel those off. And then the 980 divided by 140 is the voltage. And if you do that calculation, you find 7 volts. So that's the voltage on the capacitor before we hook up the resistor. When the resistor is connected, so we have plus and minus charge on the capacitor. When the resistor is connected, there'll be a complete path, and in conventional current, we're going to have a current head down through this resistor to reach the minus plate. That's the conventional current, the direction that a positive charge would move in the circuit. So our next calculation is to see if we can calculate the potential across the capacitor 0.882 seconds after the resistor is connected. Well, to do that, we have an equation. The potential difference at any particular time is equal to the original potential difference. That'll be 7 volts for this problem. And then an exponential, e to the minus the time value divided by R times C, the resistance times the capacitance value. So let's do this as a side calculation. R times C, we have the resistor, 12.6 times 10 to the third ohms. Ohms are the standard metric unit, so I need to put in 10 to the third to replace the kilo. And then the capacitance value, and farads are the standard for our capacitor, so 140 times 10 to the minus 6 farads. So you should do this calculation on your calculator, and hopefully you'll get 1.764 seconds. So this 0.882 is not just a totally random number. I selected this number because it's half of the 1.764. So if we start with 7 volts and we go for a time half of the RC time constant, will the voltage just be 3.5 volts? What do you think? Well, let's see how it works out. So V equals 7 e to the minus 0.882 seconds divided by 1.764 seconds. 7 e to the minus 0.5. The 0.882 is half of 1.764. Should check that on your calculator. So we obtain that, and then evaluating e to the minus 0.5, you need to deduce how your calculator handles this. On the calculator I use, I put in the minus 0.5 and then activate e to the x. But when you do that on your calculator, you should obtain 0.6065 for the value of the exponential. And multiplying these two together, we find 4.25 volts, not 3.5. This is a nonlinear process. It's an exponential. And actually, the way the voltage is changing over time, the voltage of the capacitor starts at V0 and then follows an exponential curve down towards 0. So you cannot just stop by finding the RC number in seconds and deducing what fraction of the RC has been in the elapsed time. You must go through the exponential calculation. Okay, what about if we want to calculate the current in the resistor, the time at which the current in the resistor is 0.43 milliamps? I don't have an equation for current, I have an equation for voltage. If we know the current in the resistor and we know the resistance value, can we find the voltage for our capacitor? And the voltage of the capacitor is going to be the same as the voltage of the resistor, since they're the only two circuit elements in the circuit. One's positive, one's negative. Won't bother with that. But how do we go about finding that? We use V equals IR for the resistor, and the voltage, we have a current of 0.43 times 10 to the minus 3 amps, and we have a resistor of 12.6 times 10 to the third ohms. So 10 to the minus 3 times 10 to the 3 will get 10 to the 0 power when we add those powers, so that's just a 1. So in our calculation we can do 0.43 times 12.6, and we find the voltage is going to be 5.42 volts. That's the voltage that will produce 0.43 milliamps in this particular resistor. And now we can go back to our RC equation. We want to calculate the time. We now know the voltage at this particular time. Again, we know V0 is 7 volts when the capacitor is charged and then connected to the resistor. 7 volts we start with. We already know the RC number, 1.764, so we'll reuse that. So let's go ahead and start the process here. 5.42 volts equals 7 e to the minus t over 1.764. Now I have a situation here where this t is kind of buried inside the exponential function. So I'm going to have to get that out. The way we're going to do that is take natural log of both sides. But before you take natural log of both sides, you should divide both sides by 7. So you just get the exponential on the right side. So 5.42 divided by 7, I get 0.7743 equals e to the minus t over 1.764. And now take natural log of both sides. So natural log, and again you'll use your calculator to accomplish this. Natural log of 0.7743 equals natural log of e to the minus t over 1.764. And we have a situation here. The natural log function is the inverse function of e raised to a power. So these two functions will cancel each other, and we'll just be left on the right side with minus t over 1.764. I'm going to continue up here where we have a little bit more space. So the natural log of 0.7743, the number is less than 1, so we'll get a negative, and your calculator should report to you minus 0.2558 equals minus t over 1.764. Again, the natural log is the inverse function for e to a power. These two functions cancel each other, and we just get the argument of the exponential. The minus signs will cancel. and we multiply both sides by 1.764, and we find that the time is 0.45 seconds. The time is 0.45 seconds. So that's our situation here for our capacitor. This answer makes sense in comparing to the situation up here. When the time was 0.882, we were at 4.25 volts. So, perhaps something in here. So, for the answer for part B, when the time is shorter, the capacitor is not discharged as much, and we're at 5.42 volts. So up here, the answer for C. So these numbers are consistent. When the time is shorter, the capacitor has more potential difference across it. The voltage is higher. So keep practicing with those expressions. V equals V naught, e to the minus t over RC. Make sure you use standard metric units when you're calculating the RC.